So good afternoon, everyone, and thank you for joining us for this new Break to Excel webinar. Today we will talk about WAAM and INVAR alloy for aerospace tooling applications. So I will now leave the floor to Marco and Arjun. I invite you to leave your questions in the chat during the presentation, and we will answer them at the end.
Introduce first. The title of the presentation is to tailor the low expansion iron nickel alloys, typically known as INVAR, for aerospace tooling applications for composites. Yeah, let's go to the next slide. Yeah. Yeah, no problem. Yeah, we will start with, again, a short introduction. I will speak about the application case on aerospace tooling for composites and what are the challenges there and what can additive manufacturing do to face these challenges to make it better. Arjun will then go in depth into the specific alloy, which is a really special one that you will see later in the presentation. And we will give a future outlook what might come next after this project. So yeah, next slide, please. Yeah, a little bit about Great to Excel. Lucy already explained what we are doing. Big consortium, but we have three objectives. One, to develop graded materials using wire arc additive manufacturing processes for really large scale applications. And to make it economically viable to be used in industry. So yeah, next slide, please. I think that's a little bit more in depth from my side. Yeah, my name is Marco Bosman. Studied material science in Delft some time ago. Working for about 25 years in aerospace industry. With Fokker. You see a nice Fokker aircraft that we don't build anymore, but it's still our legacy. The Fokker company was taken over by GKN Aerospace, now part of a bigger group with over 15,000 employees in multiple countries all over the world, serving as a tier one supplier to the aerospace OEMs like Boeing and Airbus. We are typically supplying wings, tails, fuselages, so parts, big parts of aircraft towards the OEMs. Arjun, you can do that.
A little bit about myself. I graduated from TU Delft in Masters of Material Science and Technology. Mainly, I was involved with building of metals and specifically specializing in additive manufacturing and also with some experience in weld metal cracking. From there on, I moved on to take up the PhD role in TU Delft, which was focused mainly on additive manufacturing of low thermal expansion iron nickel alloys. And this is within the framework of the Great to Excel program.
Yeah, well, let's elaborate a little bit of the background of this project on the use case that we are using. It's molds for making composite parts, typically carbon fiber composites that we typically use in aerospace for lightweight, very strong constructions, which we very much like in the aerospace business. But to make these kind of parts, we use molds to make the shapes. And this is typically the process that we are using. We have a stack of composite material plies, which looks like a fabric type of parts. We stack them together in a certain sequence that we design such that we have the properties of our composite components, right? We mold it. In this case, we inject a resin in it, but we always need a resin or a matrix material to hold the fibers together. We release then the part from the mold after a curing cycle where the matrix hardens and you get a really solid part which doesn't feel like a fabric anymore, but as a really hard, stiff material. Next slide, please. Yeah, and I will show some of the examples. This is within GKN Aerospace of a typical fuselage. You see a bit of the sizes that we are facing in making composite parts out of one single piece. This is a fuselage of a business jet. And we have another example. Next slide, please. Is for making wing spars or spars for tails. On the big picture, you see a 17-meter long spar which came out of a double-sided tooling. On the left picture, you see an automated layup of such a piece on top of a mandrel that's made of INVAR material, because for these kind of sizes, we typically use INVAR material, and I explain a little bit about that, why we are doing it later. But the next example you see here, instead of the wing spar, you see the complete wing cover on the real size that we are making them, that Airbus is actually making them. This is not a GKN picture, but here you see the size of the components that we typically work with in aerospace. This is all iron nickel alloy that we are using to build this huge tool to cure the composite wing skin which you see above. This is about 30 meters long. Yes, and the challenge is why we are using iron nickel alloys, because that's a really special one, is because we need to match the thermal expansion coefficients, or actually to be more accurate, the thermal shrinkage after your cure cycle to room temperature when it's still inside the mold. We have to match the carbon fiber part with the mold material. Typical cure cycle you see here, you see a ramp up of temperature, you see a plateau on a certain temperature, and that depends on your resin system that can be between 150 and even go up to 400 degrees C, depending on the matrix material that you're using. And then we have the cooling down, where which is the most critical of the whole cure cycle, because there is where you determine your shape of the composite part, and that should come along with the mold. And here you see some materials that can be used for molding. You can use a steel mold, and you see here when you elevate the temperature, the steel will expand more than the carbon fiber, and it will shrink more, going back in the last phase of the cycle. If you use aluminium, it will get even worse. So these materials are not really useful for the application, typically not with very large parts, because you can imagine that the thermal expansion differences between the carbon fiber material and the steel or the aluminium will become so big, will become very big when you have meter scale components. You are talking about centimeters of mismatch, which could cause cracking depending on the mold geometry. And it could cause definitely inaccuracy of the carbon fiber part shape, which is in aerospace pretty accurate, because we are needing pretty accurate tolerances on our aerodynamic shapes. So if you see the green bar, you see a really special metal. It's INVAR. It's the iron nickel alloy, which hardly expands with increasing temperature. And that is the a reason why we are using this for our carbon fiber composite parts. But it has some special tricks around it, why it behaves like this, because this is not normal for a metal to behave. But Arjen will talk a little bit of that. In the next slide, I will explain a little bit more on the requirements for molding and why we are pursuing additive manufacturing as a potential technology to build these kind of parts. Well, on the top you see the main requirements that we have for certain tooling. So your mold surface should be very accurate, and it should maintain accuracy during the whole cure cycle, so during the heating up and the cooling. So a high thermal expansion doesn't help here, specifically in complex curvatures. It should be stiff enough to withstand the pressures during the cure cycle, because typically we are using pressures like 3 to 6 bars to cure the part within the mold. We are using vacuum to get all kind of porosity out together with the pressure. That helps a lot, and because we are using a fabric type of part, we need this to get a little porosity in our composite part, so it's the mold should be vacuum tight. Because we are doing a cure cycle with heating up and cooling down later on, we are needing heating and cooling elements, specifically when we have a kind of double-sided molds that we don't put in a big oven like an autoclave or whatsoever. We tend to go out of these kind of really large capital equipment and go more on multifunctional tooling where we include the heating and the cooling. So all in all, that makes the tooling geometry relatively complex. And there is where AM comes into place, because AM gives us more design freedom to get all these features right. It enables you to use less material to make the same part, because we can typically, what we do conventionally is we machine mold shapes out of big blocks, and we cannot really hollow it out or make more kind of bionic shapes that you can do with additive manufacturing. Reducing material, that's reducing your material waste during machining, of course, but also your total usage of material, and also being more energy efficient by having less thermal mass on your tooling. A very big advantage that we see on our INVAR tooling using AM is the short lead times that we get, because you can for big sizes we are facing lead times sometimes from 6 to 12 months for big plates that needs to be specially made for our purpose. Wire arc additive manufacturing only uses wire, which is readily available. But the final thing that we really want to explore beyond all these advantages is to see how we can tailor your material properties when we are building this part using additive manufacturing layer by layer. You could tweak your material too on locations where you need certain properties, for instance. And that is what we see as a bit of the holy grail, the step on the point on the horizon. Let's call it like that. What is actually AM will offer us what we cannot do today. And Arjen will share some of our initial steps towards this.
Thank you, Marco. With all this information about iron nickel alloys, I will actually start by introducing you to what this material is. Why is it so special? So on this slide, you see a plot which shows you the variation of the thermal expansion coefficient versus the nickel content. Now, in essence, INVAR alloys comprise of iron and nickel, and these alloys are known for their extremely low thermal expansion properties. So as you can see, at around 36 weight% of nickel, you get a very sharp dip in the thermal expansion. And this material is therefore referred to as INVAR, which stands for invariance to temperature, meaning that it does not change its dimension when it is heated, but this behavior is only maintained up to a certain temperature. Further on, when you increase the amount of nickel content, you can get different low thermal expansion alloys. For example, if I go from 36 to 42, I can have an alloy which is called INVAR 42 or alloy 42. And the thermal expansion properties for this alloy are retained up to a higher temperature. Now, typically, if you were to take a piece of INVAR and heat it, you would see a behavior which up to a certain temperature range shows almost zero thermal expansion. And if you compare it to a normal metal, you can see that the difference is massive, which is why these materials are preferred in aerospace tooling applications. Now, a little bit on the background of what wire arc additive manufacturing is. As seen in this figure, in wire arc additive manufacturing, you use a controlled electric arc, and which provides the required heat that is used to melt metal wires. And when this system is combined with a multi-axis motion system, it allows you to deposit 3D structures. In this figure, you can see the schematic of the process, whereas in reality, if you were to go look at the process, which would look something like this. You have a metal wire, which is incoming, and then you have an electric arc, which is depositing the material layer by layer. Now, this process is repeated again and again in order to generate the required 3D structures. With this, we moved on to additive manufacturing of INVAR 36. We started by depositing blocks around 20 millimeters in height and 100 millimeters in length. The first thing that we found was that after cutting the blocks was that they were very prone to cracking. And as you can imagine, these cracks are defects. So our first step was to how we can avoid these cracks. In the figure below, you can see it shows you the total crack length against the heat input. Heat input is a term which is used in wire arc additive manufacturing, which specifies the amount of energy that is going into the material, or in simple terms, the amount of heat you're putting into the material. Now, at high heats, we found that the material was more likely to crack, whereas when we started to optimize the parameters, the amount of cracking reduced, and finally at a certain heat input or a certain process setting, we were able to achieve deposits which were free of cracks. Now, why do we not want cracks? As you can see, the next step was to characterize the material for its tensile properties. Now, we took samples out of the blocks that had cracks, and we started testing them. As you can see, the blocks that had cracks in them performed very poorly. And an example is shown on the figure below, where when you start pulling on them, the cracks that are already present in the material, they start to open up. Whereas in the case when you successfully can avoid cracks, in that case, your material actually performs how you want it to perform. This was a good starting point for us, as we were able to achieve crack-free deposits. From there on, we moved on to our next step, which is also another advantage of wire arc additive manufacturing, that it allows you to incorporate multiple wires in the single melt pool. Now, the idea here is that by incorporating two wires, one is just an INVAR wire, which I mentioned earlier consists of 36 weight% nickel, and another is just a nickel wire. So by mixing the two wires in a specific ratio, you can change the composition as shown below, from 36 to 42 or to 48 or whatever you desire. However, initially you have to optimize the process, and one such condition of the optimized process is shown here. You can see very clearly, like, the way we optimize the process, we feed two wires in the single melt pool, and by varying the wire feed speeds, you can obtain the required thermal expansion properties. Now, this is a very good advantage of wire arc additive manufacturing, as in order to reduce lead times, like Marco mentioned, you can use this technology to deposit whatever composition you want. In the next step, we deposited different low thermal expansion alloys. We deposited a block which comprised of different low thermal expansion alloys. We started from INVAR 42, we moved on to INVAR 46, and then finally to INVAR 52. The first step was to cut the material and see if we have any major defects. And a result is shown in the figure on the right and below, where you can clearly see that the cracks which we had earlier in the single wire deposits were avoided. The reason for this was that we had already optimized our process parameters to maintain the lowest amount of energy that we require. And by doing this, we can avoid major defects like cracks or other defects such as porosity and everything that are very commonly found in additive manufacturing. And earlier, we have also seen that having these defects is undesirable, as you can imagine that when you start using this material in a loading application, it will very likely fail before it is required to. Moving on to a more important consideration was to analyze whether the materials that we are depositing are actually being obtained. For this, you start to take your sample and analyze the chemical composition at different places. And when we did this, we clearly found, okay, our deposited material comprised of different chemical compositions. 3 distinct regions were identified, which corresponded to the desired compositions that we wanted. The first one was INVAR 42, the next one was INVAR 46, and the last is INVAR 52. By doing this, what we do is we have a good control over the desired compositions that we want. And also another important thing in this case is to have a gradual transition from one composition to the next. This is very important in order to avoid compatibility issues within different materials, because if there is a sharp transition, you can imagine if one material expands less compared to the other, and there's a sharp transition between two, it will very likely lead to cracking. But by using wire rack additive manufacturing with 2 wires and in a controlled manner by optimizing the process parameters initially, you are able to achieve a smooth transition from one alloy to the other and also deposit the desired compositions that you want. The desired compositions are further analyzed chemically, because another aspect of feeding multiple wires is, okay, whether your material is mixing properly or not. Because a common problem during welding can be related to segregation, which means that when you try to feed different materials, they are not really mixing and just separating into one another. But in this case, because of the compatibility between iron and nickel, you can clearly see that across the wall and also for different compositions, there is very good mixing between iron and nickel. The red figures correspond to the amount of iron in the build, whereas the green ones correspond to the amount of nickel. And there are no segregated regions where you have a clustering of a particular element. And this was very good for us, as you can have a good control over the deposited compositions. Overall, what this gives us is a very nice precise control over the compositions that you want, and also the mixing that can be achieved during the dynamical nature of the wire rack additive manufacturing process. Finally, we look at the thermal expansion properties, and which is shown in the figure below. The first curve, the blue curve, corresponds to the thermal expansion of just INVAR 36, which I mentioned like earlier, up to a certain temperature, up till a certain temperature of about 150 degrees, there is almost no thermal expansion. However, if you want to go up to higher temperatures in order to cure your composite parts, you would require an alloy which is much more stable than that. In that case, you might want to use, say, alloy 42 or alloy 46. In this figure, you can see an example of how the thermal expansion of alloy 46 is much better than INVAR 36 after a temperature of around 350 degrees. And in this case, the alloy is deposited by using twin wire additive manufacturing. This gives you a very nice control over the desired compositions you want, and also it gives you the possibility to obtain on-demand thermal expansion properties. I think with this slide, I would like to wrap it up with our future plans.
Let's take over here. I think, we now learned about what iron nickel alloys can do and how you can play with the thermal expansion coefficient. And that provides the potential of specifically tailoring or creating your alloy that perfectly fits your cure cycle. So if you go for a certain temperature, you could choose your iron nickel composition to get the best match, to finally get the highest accuracy composite parts out of it. You could also look at locally changing your composition, where you then locally change your thermal expansion behavior, where you can, for instance, use that for geometries that needs to be released easily from your mold. That's you can let the mold by expansion, letting it open or close on specific locations. Besides that, I think additive manufacturing, that's not what we showed today, but that's an addition on it. We can use topology optimization to reduce the amount of material that we use. But if we can do that together with the actually go back to that, the topology optimization typically we are doing for mechanical properties to reduce weight of the part, still withstanding your loads. But if we can also use our thermal behavior together with the composition in this optimization, we can go even beyond that to even reduce much more material to simulate for both the mechanical and the thermal behavior. So that's future work. We showed now that it can be done to tailor INVAR alloys towards a specific expansion that we need, and that opens up a lot of opportunities for the future.
Yes, so with this we end our presentation.
Yep.
Right. Thank you.
Thank you. Thanks a lot to both of you for the very insightful presentation. We can take questions. So for the participants, you can either write in the chat or you can ask your question. Well, Hun and Marco. For now, I don't see any question in the chat. Has anyone a question to ask? So Sarah is asking, where do you use WAAM in France?
Yeah.
It's
Well, it's a good one. I think, and the nice thing is within our consortium, we have Naval Group inside that is actually doing WAAM at their factories. But I'm pretty sure there will be other places too that they are using this or exploring this technology. Because
yeah, for sure, yeah.
Yeah, because the equipment that you actually need for this is not very special. You actually need a welding robot, and if you have a welding robot, you could do wire arc additive manufacturing if you understand the process well. So there are several parties also within France that are exploring this. Among them is Naval Group.
Yeah, indeed, Naval Group in Nantes-Andret is part of the consortium, and they are actually producing 2 of the demonstrators of Grade 2 XL project. There is a question from Maxime. Are the scientific results enabling to foresee an industrial exploitation? Is GKN Aerospace planning to use such multi-material molds in the future?
Yes, in the future, for sure. but to be honest, it's still a long way to use this on really the size that we need in our company. But we are making great progress here. We are going to show it on a demonstrator mold within the Great to Excel project, which is about almost 2 meters long. Yeah, that's a good start towards real applications. But we need to go bigger than that, and we need to mature the supply chain that it actually can do this.
Thank you, Marco. Nice to hear from you. Can you hear me?
Yes, I can hear you, Maxime.
And thank you, Arjun, for the presentation. Yeah, I was wondering, as RAMLab may be producing your demonstrator during the project, if you were foreseeing industrial application, would you go producing such molds in the future with RAMLab, or would you require more industrial partner?
Yeah, we actually require more industrial partner. It's just when it is real tooling that we are going to use for aerospace applications, we need to have a firm supply chain with all the certificates that comes with that. Our partner RAMLab here in the Netherlands, that are going to build the demonstrator. They're not an R&D organization, but what we call in the Netherlands is a field lab. It's somewhere between R&D and industry. So we still need to get the final step.
Yeah, indeed. Thank you for your answers. Nice to hear from you.
Yeah.
Thanks, Maxime. There is a question from Antoine. Between your INVAR mixes, did you need to adapt the electric parameters?
I think I can answer that question. Initially, we did optimize our parameters. So the way the wires are being fed into the mid pool, I think I showed you a video earlier. Can you see my slides?
We can see the final slide.
Okay. I can show it to you again. Do you see this slide and the video that is being played? Okay.
Yeah, we can see the video.
So in this, to get to this, we initially went through a lot of trial experiments. So the first thing that we fixed was the feed speed of the wires, the ratio in which they are fed, and also the positioning of the wires regarding the arc. And then once you optimize that, and then the parameters were optimized to get a stable bead, so they can be overlapped in order to avoid any defects. I hope that answers your question.
Thank you, Arjun. And we have another question from Elia. I'd like to inquire about managing chemical composition, specifically regarding controlling the percentage within the process. And additionally, I have a more technical question. What are the welding parameters that might impact the chemical composition during twin welding? Do you see the chat?
No, but I think would.
So the managing chemical composition regarding controlling the NI percentage within the process.
Yeah.
Once again, I'm reading the question. Yeah. So regarding the first part of the question, which is managing the nickel percentage in your process, I think if your question is related to how well it mixes and how well we can manage, I think that is related to the part if you have a stable feeding of the two wires taking place or not. If you have both the wires being fed in a stable way, then you can obtain a good control over your composition. And In addition to that, it is the solid solution compatibility between iron and nickel, which makes it feasible to have mixing during the process itself. And moving on to the next question, which is what are the welding parameters? Mainly, I think you can combine the welding parameters in terms of the heat input. And also, when we are talking about 3D printing, another important parameter is your interpass temperature. I think interpass temperature along with the heat input has to be controlled in order to avoid defects. And also, if you are grading, if you have a graded structure, or in the case as we had, in which different alloys were combined. So if you have excessive interpass temperatures, there could be a possibility that in the final stage, what you get is a single composition because of diffusion of nickel between low and high areas.
Thank you.
Sarah.
And yeah, there is
Yes,
another question.
the first paper is published, I think, which is regarding the single wire additive manufacturing of INVAR. It is available online. And the next step of the results, which are related to the twin wire arc additive manufacturing, are in the process of being published. If you
And
want,
all the
yeah, go
sorry.
on. Yeah.
All the scientific papers published by the project partners are also available on the Great to Excel website. There is a section with the links to the published papers. And there is an additional question from Elia. Is there a negative effect on the microstructural properties due to this chemical gradient, unlike thermal expansion?
In terms of microstructure, no, because if you saw earlier, between iron and nickel, there is a single phase austenite region present. So if I move on further from 36 to 8% of nickel, then you will still have a single phase microstructure that will be available to you. However, like I mentioned, if your parameters are not controlled properly and you result in some kind of segregation, then you could end up in a dual phase INVAR, which is unwanted as it impacts your thermal expansion properties. But between iron and nickel, there is complete solid solution solubility, and by mixing them, you do not have any negative influences on the microstructure properties. Elia, does that answer your question?
Yes, it's clear. Thank you.
Okay, no problem. And then
And there is another question from Sarah, yeah, about interpass temperature. What you use to do you use to control it or to reach this temperature?
To control it, control the temperature, we use thermocouples. So thermocouple is attached onto the material itself, and then it is capable of giving you temperature readings up to 1200 degrees Celsius. So once we know that the desired interpass temperature is reached, we start depositing again. The way you have your interpass temperature is because of the process itself, because the arc is very hot and you're depositing hot metal, and it eventually heats everything up. And we just wait for it to cool down to reach a specific temperature. For our case, we were using a maximum interpass temperature of 150 degrees Celsius, which is on the limit of the recommended interpass temperature for working with environments. And I think Lucy shared the link from where the paper can be found.
Yeah, exactly.
Yeah.
Okay, any other question? If not, I will thank Arjun and Marco for the very good presentation. Thanks a lot for sharing your expertise. Thank you to all participants for the many questions and the good interaction during this webinar. We really hope you enjoyed it. I will just share a last slide to show you, to invite you to follow us, to take a look at our website, to follow us on LinkedIn. You can also contact me anytime if you have any question, if you want to be put in touch with our consortium members. We will organize more webinars in 2024, so stay tuned. And thanks again for being with us today. So I think we can close the webinar and see you next time.
Thank you. Thank you for attending.
Thank you, Lucy.